So with this background, which was not necessary, but I was just warming up, we have the astronomers' measurement agenda again. To remind us ourselves, we are interested in measuring the intensity as a function of these attributes. And we now ask what is the difference between what we were used to earlier, like the optical measurements. When we come to radio wavelengths, whether things are same or do they differ in an insignificant way. And so we will look at one of the first aspects that hits us is that we have now come to very low frequency, and the typical photon energy h nu is going to be very, very weak. It's too weak to be detectable individually. There are no detectors like we have in optical wavelengths. It doesn't cause any reaction in a matter that is exposed to this radiation where radio photons might be falling on it. So we are stuck. We are without any so-called detectors that we can use, where each photon would have done something interesting and we could have counted the effect of large number of photons by the corresponding proportional effect, and we would have got some measure of the intensity. But fortunately, we can appeal to the feeble dance that the electrons in the metal exposed to this radiation would do, and which will induce effectively some current. And this oscillating current, where the dance is dictated by the electromagnetic radiation received or the photons at radio wavelengths incident on this matter, we will have this current measurement possible. And as we will see, we have large photon density. We can use classical description, and that we will be using all along almost. So we can sense this current somehow, and we can amplify it and record it, and that's how we get the information. As I said, the individual photons are too weak to do anything to this exposed matter, so we have no detectors, where even a swarm of billions of these radio photons cannot free an electron from its atom. As you know, this is a quantum interaction, or cause any photochemical changes like we have on the photographic plate. So we will depend entirely on the induced currents in what we call pieces of metals, which are often called antennas. So we will duly amplify this with high fidelity and amplify them enough so that we can record it. So antennas come in various shapes and sizes. You can see very familiar examples of your TV aerial that you used to use earlier in olden days. Jansky's Discovery antenna is one starting example of it. And you can use horns, various shapes. You can put such sensors or transducers at the focus of shaped reflectors, where the energy coming or radiation coming from a given direction is brought to a single point, finite size, which is dictated by effectively the image of radiation coming from that direction. You can have a variety of sizes in it, small things that you put for your TV dish, and going all the way to big sizes, not limited to the size that is shown here, but steerable dishes and so on and so forth. So when you put something at the focus to sense for a shaped reflector, it's as if you're sitting there and viewing the dish surface of that reflector. And you will find that the way you look at the dish surface will dictate what will be your ability to sense radiation coming from different directions. The typical width of your response will depend on the size of of this reflector, and not on the sensor size. The sensor size will decide how you look at this reflector, because you're collecting light from the entire reflector surface in some way. So the way you look at it might differ. You may not look at it with the same weightage from all parts of the reflector. You might reduce the importance of the radiation coming from the edges of this reflector, because if you had given large weightage, then as you go outside the edge, you will be looking at the ground, and which is something you want to avoid. So at the cost of losing some important collection of photons from the edges, you make sure that you don't look at the unwanted region in the view, which is the ground. So you see predominantly the reflection of the sky signal from this reflector coming at the focus, and that's where you put those sensors. There are various mounts used for steerable antennas. Will not go into the details, but you can have something that is defined with respect to the local coordinates. That means the local vertical, or angle with respect to local vertical, versus you can define things with respect to overall Earth system, where the rotation axis is the reference and the equatorial plane being perpendicular to it. You can define the declination with respect to the angle the source makes with respect to the equatorial plane, and measure hour angle along the time axis as the Earth rotates. Okay, let's ask ourselves, what are we really looking at? We then realize that we are looking at pure random noise from the sky. If you were to look at this pictorially, there is a familiar example that you would see in olden days. When there is no signal coming through your antenna that is connected to your TV, you will see this speckly bubbling pattern, which will vary randomly, and the bright and dark spots will dance around randomly. And that's really the kind of information we have coming from the sky. It's mostly random Gaussian white noise. I will explain each one of this. Random is very easy to understand. That means you cannot predict what is next. It doesn't depend on the previous history. Gaussian is the description of the statistics that it follows, and the whiteness is the description of the spectral information, the color of it, whether it has any particular color or not will be described by the spectral content. And so white means that all wavelengths or all the frequencies within the band have statistically equal intensity. What we receive, and we might collect it with all this arrangement of shaped reflector and bring it to the focus where we have the sensor. What we will actually see is a random fluctuation in the current, and we can pass that current through a resistor or something like that and measure the voltage. It doesn't matter whether you refer to it as current or voltage, as long as it's proportional to the electric field of the electromagnetic wave received. And that's what we try to measure. Then, of course, we will require, since the signals are very weak, and we'll see how weak they are, we will require some way of amplifying them so that they are large enough in amplitude that can trigger or can be recorded on usual devices. It could be on a computer or a chart recorder or whatever it is. Typically, it has to be brought up to the level of at least few hundred millivolts from very, very tiny signal that we receive. To repeat again, we are measuring sky noise. So the signal for us is the noise that was noticed by Carl Jansky included, and other communication people will also consider this as a nuisance. So this is the noise for others, and it's the signal for us. Be measuring necessarily the statistical properties of this noise because it doesn't have any particular pattern. It's a random phenomena. So we can ask what is the mean, what is the standard deviation or variance of this noise, whether there's any color dominating, and what is its probability density function. If whatever pattern we are receiving, no matter how random it is it similar when somebody else standing somewhere else looks at it, and we compare notes, whether it has any pattern or repetition or similarity when we look at it in time, and so on and so forth. If we look at the statistics, since we are treating these as random fluctuations, we can go to the basic entities that make this radiation reaches, which are photons. We can show that photons follow Bose-Einstein statistics. That's what they call bosons, which this statistics is a simple combination, can be stated as a simple combination, but it's very complicated when you work out the maths, where you have the expected number of photons, which can vary at intervals of time, which can be related to the bandwidth. To be precise, inverse of the bandwidth. The bandwidth is in hertz, and you can take 1 upon the bandwidth, which will give you a time scale. So whenever you look at a certain range of frequencies where we associate width of the band in so many hertz, we can know that there will not be variations in whatever information we look at intervals narrower than the inverse of the bandwidth. So information will change only at the rate of bandwidth, and we can ask what is the number that we get. So the expected number of photons changes at these intervals, and it changes randomly. We can ask what distribution that number is following, and it can be shown that it follows an exponential distribution. That means you will find the zero photons is actually more likely most of the time. More often than not, you will have a small number of photons, and once in a while you will get large number of photons. This is called wave noise. This can also be described in terms of electromagnetic wave associated with it, if we can use a classical description, where the complex field, electric field of the electromagnetic radiation received will have real and imaginary parts, and you can show that the real and imaginary parts follow Gaussian distribution, bell-like distribution, which is also called normal distribution, with zero mean and some variance, which is in fact the intensity that we have here. So if you take the number of photons and multiply that by h nu, you will get the intensity here. So you can represent it in any fashion. The essential dependence or the statistics remains the same. So the real and imaginary parts, when squared and summed, you will get the intensity. So you can show very easily that when two independent variables have Gaussian distribution and you add their contribution after squaring, the entity you get, which in this particular case is proportional to the intensity, will follow exponential distribution. But while we expect certain number of photons to be received, we have, let's say, identical experiment. The same number of photons were expected to be received in, let's say, more than one places. You will find that the actual number received might differ from one case to the other, or one instant to the other, or one location to the other. And this, the variation in this number from or departure of the number actually seen from the expected mean number of photons at that given time, which is dictated by this, which itself follows the exponential distribution. One of the realizations of it will now follow Poissonian distribution. So this is called counting noise. That means you expect 10, but you get typically 10 plus or minus square root of 10. So n plus or minus root n. is the typical number that is expected when n is expected from these considerations. The n itself is the deviation from the mean number that is expected, which is sort of a steady thing, and it's the descriptor of the mean intensity of the source in terms of either number of photons or the mean intensity. So you have two things operative. You have number expected at any given time at intervals of inverse of bandwidth, varying in a fashion that is given by this exponential distribution. And even when you expect n prime, you will get variation about that, which is a Poissonian distribution. So one thing is to note before we go further is here for this distribution, the mean and standard deviation are same. This is the property of the exponential distribution. Whereas the Poissonian distribution, you will find the mean and the variance are same. Please distinguish between standard deviation and variance, which are related by square of 1. So variance is the square of the standard deviation. And we'll use this in the subsequent discussion. So one is called the wave noise, which is this random fluctuation following exponential distribution. And the other one is called counting noise or Poissonian noise. Which one dominates? Each time it's a combination of the two, of course. The number that we get is dictated by both these distributions. And the overall distribution is, as I said, is Bose-Einstein distribution. Which one dominates depends on the number of photons we receive. As you have seen, that we have the typical fluctuation that we will see in the number received will depend on both these processes. One of them had the variance. If you write the variance of the net process, it will be combination of the variance coming from one process, which is the wave noise, where you will find that the standard deviation was proportional to number of photons, and so variance will be square of the number of photons. Whereas in the Poissonian process, the variance itself was proportional to the number of photons. So it will be a combination of these two. And as you can see, which one will dominate will depend on the n, the typical number of photons expected, which is in terms of the occupation number. You will find that when the n is very small, less than unity, you will find the RMS is dominated by the counting statistics. And this is the typical regime that you encounter in optical wavelengths where your photons starve. Whereas in the Rayleighian regime, you will find that NS is largely greater than 1 unity, and you will find then you can ignore the term associated with the counting statistics, and you will largely have RMS which is proportional to the number of photons itself. There is no exclusion principle relevant here. The situation in these two cases can be described through this cartoon, which I'd always love to show, where each piece of packet, which consists of number of photons, which are large in radio, and they differ from each other in some random way, followed by this so-called wave noise. And the information is distinct only at the interval of 1 upon the bandwidth or larger. You cannot see any difference within the packet width. So if you use 1 megahertz bandwidth, for example, these fluctuations will be seen at microsecond level. If you use gigahertz bandwidth, you will see these fluctuations at nanosecond level and so on. Similar thing in optical, you will find you have most of the bogies empty. Once in a while, you will have a photon or two, thanks to the Poissonian fluctuation. Okay, so as I said, at radio wavelengths, we can safely use wave description, and we'll refer to all the aspects in terms of the electromagnetic radiation, where we will refer to electric field component of the radiation received. We will also see what property it has, and one of the important attributes of descriptors of this radiation and the electric field is this complex nature of the field received. And most importantly, now we have access to the precious entity called phase of the signal, the phase of the wave. And earlier, in where we were appealing only to the intensity, the phase information was completely lost. We had modulus square of the complex information that we get at radio wavelengths very readily. So this is one of the biggest advantages that we have in radio. We can measure phases, we can compare phases of radiation received at different locations, at different times, and so on and so forth, and gain a lot of information through that, and ability to among various things, pinpoint the directions of the sources accurately. I must have mentioned earlier, and I repeat, that what we have is Gaussian statistics of the real and imaginary parts of the complex electric field that is received. And you might wonder why it is Gaussian. And there's alternative justification for saying this readily is, if you look at the number of radiators, no matter how narrow cone you might take to look at when you look at the sky, a large number of radiators radiating towards you from that direction sector, you will find you have uncountably large, although finite, large number of uncorrelated contributors. They are not talking to each other. They cannot conspire because they have no way of communicating with each other, given their large separations in spatial distances. So when they are radiating together, or when we view their radiation together while they are not talking to each other, you can show, appealing to the central limit theorem, no matter what distribution they individually they might have, collectively their combined effect, sum total, will follow Gaussian distribution, normal distribution. So this can be also thought of as, even if you think in terms of sinusoids that you have, large number of sinusoids added with different amplitudes and different phases which are not related to each other will also lead to similar description of the signal and the statistics resulting from it. So this is again repetition of it. Here I'm just counting the number, the attributes. So intensity is 1, 2 sky coordinates, making it a total of 3 things. And this is basically intensity as a function of these 2 coordinates, frequency, time, and polarizing state. So we have 6 parameters here, or 6 entities. And as I said, span and resolution in this 6 parameters define the vital statistics of a telescope. What is possible in terms of what span is possible, what resolution is possible. So whenever you look at a radio telescope, you can, or any telescope for that matter, you can ask. This is, some of these questions are the ones that you ask when you even buy a camera. You ask, whether it can record bright light or dim light together, how well it can do that, how well it can see in dark, what is the resolution it has when I take a picture with my camera, what is the color contrast, what is the range of colors, is it a black and white or does it have different colors, and you can see if you need to make a movie of it, if things are changing as a function of time, or give long exposures, in which case you will see different effects if the picture is changing. And then you can put a Polaroid in front and you will see whether the light was polarized or not. So this is nothing new in terms of the kind of attributes you do take into account. So as we know, in the case of the camera that we buy, these days they come in even on your cell phones. You ask how many megapixels it has. What does it tell you? Basically, it tells you what is the fineness in the pixelation of the picture, which amounts to resolution. Of course, that is dictated by the lens as well. You cannot beat what the resolution that your lens has dictated, which is dictated from the standard optics that we will be discussing, and which is relevant even in the radio, which is lambda divided by d, will give you the angular resolution. But then you also ask whether it can record, it can take panoramic view, and so on and so forth. You worry about the span. So basically, essentially, all the considerations that you put in while you buy your mobile camera are likely to put it here as well, and be greedy, right? You want best of everything. You want largest span and finest resolution in each one of these. You should be able, you want to be able to distinguish in intensity of one source from the other, even if it differs by a slight amount, and so on, or measure it accurately. You will find that this greed is not allowed in an unlimited way. Some amount of greed is okay, but beyond a certain point, your greed is limited by considerations of uncertainty principle, and that Heisenberg's principle will tell you that you cannot be simultaneously be greedy about certain combinations of things. So you will find that you will have certain parameters which are related to each other, like the momentum and position. You know that you cannot specify the position and momentum simultaneously more accurately than certain limit. Similarly, you can have a pair of, another pair which can be easily derived or inferred from the same thing is energy and time cannot be spelt out with more accuracy simultaneously in combination. So the same thing is at the heart of some of these relations. You will find that the angular response, your ability to pinpoint a direction or look at a selected part of the sky with preference cannot be finer than the size of inverse of the size of the aperture that you use, which in the case of big dishes with a focus will be the dish size, or in the case of arrays on the ground looking up, it will be the size of the aperture directly. Or a simple aerial might have its effective size. And these sizes in units of wavelength will dictate the fineness in the angular domain. Similarly, you will find like these Fourier relations exist, which can also be tied with the uncertainty principle pairs. You also have one important Fourier relation, which we'll look at in greater detail, is the brightness distribution in the sky. The picture that we look at of the light coming from the sky is Fourier related with what is called spatial coherence function. And this is, in simple words, is simply the level of similarity of the radiation received at a pair of locations. So if two people stand somewhere and receive signal from the same sector in the sky, you can ask how similar it is. And this level of similarity will be dictated by the brightness distribution. You can see that if it is a compact single source in the sky, you will find there will be large coherence, a very high degree of coherence in the signals received. As you get more and more sources, the similarity of signals received in the two locations will be less and less. And the extreme case of like the 2.7 degree Kelvin background radiation, which is coming from all over the sky, will hardly induce any, ensure any similarity between signals received by the two observers, even though the source of radiation is the same. It's just the different combination of radiation received from different directions that one observer sees, which differs significantly from the linear combination that other person sees. And so when you exchange notes, it's like with the same ingredients, if you make two different dishes, they might taste very different. You have similar relationship between spectrum and temporal coherence, which is basically essentially the energy time uncertainty pair. Similar relationship can be stated in terms of the spectral response being the time window. So here the width in one dictates the fineness in the other, and vice versa, and the similarity in one domain or the width over which things might appear similar or correlated, it will depend on the details of the spectrum. as you know, or we will look at it in more detail, you will find if the width of some description in one domain is something, the corresponding description in the other domain will have a width which is inverse of the width in one domain. And we will come across this in variety of ways and variety of pairs of parameters which are Fourier related. So even for a single photon case, even without appealing to the classical description, we can begin to appreciate that there are certain unavoidables and relevant aspects of the uncertainty principle that will limit the fineness with which we can do things if we have certain fineness that is expected or imposed in one of the domains. For example, here, if we collect photons across the size of the aperture, which is, let's say, d, we are allowing the uncertainty of where it actually fell within this aperture. And this gains us the ability to pinpoint the direction from which essentially the momentum component along x. So for a given wavelength and the photon energy, you can write down the corresponding momentum, which is h nu by c. You can take its component along x, and delta x is the uncertainty you have allowed in the x direction, and the component of the momentum in x will be the photon momentum times sine of theta. And if you say there's no uncertainty in the wavelength, that will translate to uncertainty in sine theta, and for small angles, sine theta can be assumed to be comparable to theta, and then you can get a constraint on the delta theta, really speaking, which you can work out the diffraction formula from simple considerations of uncertainty principle application. Similarly, along the path of the photon, you can take a section and say, if I say the photon is within this position range along the path of the photon, if I allow that uncertainty, can I specify the frequency more accurately? You can see that this argument will allow you to derive the uncertainty principle associated with or by applying the uncertainty principle in energy and time, you will be able to get the description of how fast a filter with certain bandwidth can respond, or how much detail you can see when your signal has gone through some filter. The variety of context this relation will come in.